Perfect. All right, so my name is Stephen, and I work in the Department of Physics, and I'm going to talk about smartphone-based AR for labs. I'm going to touch on the introduction, motivation, tell a little bit about what augmented reality is, and then talk a little bit about magnetic field representation that we used and future directions. So, what's the introduction and motivation? How this relates to open educational resources is we wanted to convert the physics lab manuals to open educational resources. This is actually very simple because they're written in LaTeX. So as soon as we copy and paste it into a repository, anybody can change it, and it fits very well with the community and the spirit of the physics discipline. Part two, however, though, is the lab manuals aren't as useful for online learning as they are in the lab. So we wanted to develop some resources that would improve that, add value for students working from home, and create learning opportunities for non-students, really anybody who could access this. And one of the ways we wanted to do that was using augmented reality. Now, you've probably heard about augmented or virtual reality. Virtual reality is where you're fully immersed in a simulation using a headset, usually attached to a computer. Augmented reality is a little more mainstream. On the right, we've got a Pokemon Go, which had a bit of a craze a few years back, and it makes Pokemon, little characters, appear on the surroundings. So it overlays digital content onto the physical world around you. People also use augmented reality in headsets. Here's an example of the HoloLens overlaying a bunch of cartoony things onto someone's room. A lot of this was inspired by an application that has been developed by Dr. Paul Lapointe, who's a professor in, I believe, biology, and he developed something called Cell 101, and I really encourage you to check it out. And the advantage of it is that augmented and virtual reality allow you to see something from all sides. It gives you a real three-dimensional representation of what's going on. We thought, well, this might be really useful in physics because, particularly with smartphones, we can leverage technology that students already have. And it works well for spatial reasoning. Whoops. And there's a lot of spatial reasoning in some physical concepts, and it's good for visualizing invisible things. What we chose were magnetic field representations. So here, this is the textbook that students are using right now this semester, Sears and Zemansky's University Physics, and this is how magnetic fields are represented. And this is fairly standard. Inherently, three-dimensional behavior must be displayed as two-dimensional on a page, sometimes on a computer screen. And so it's difficult to get a feel for how these things behave in real life, their full extent, and to understand how the magnetic field extends in space in all three dimensions. So we wanted to use augmented reality for this. There are some applications that already exist. Some are proprietary, and that was a no-go for us. Some are open source, but there's nothing comprehensive, completely put together. There are lots of bits and pieces that somebody worked on, for a little while and then let sit or never continue to develop. So we wanted to develop an open source app that fit our purposes. To do this, we used OER funding to hire a comp sci intern, Jared Mahoney, who developed what I'm about to show. So this is stage one of the application. This is viewed through a smartphone screen, and we can see Jared's hand holding a QR code, which acts as a marker. And there's a virtual magnet. That magnet, the blue and red, is not real, and neither are the arrows around it. But they show the magnetic field around this sort of a magnet, and we can see that Jared can turn it and look at it from different sides. So that's pretty cool. But, it's still a 2D representation. So this was the second stage, having a 3D representation. Now we can see the actual three-dimensional structure. We can see that there are magnetic field lines extending above the magnet as well as beside the magnet. And Jared can rotate it and view maybe the field from the end, the field from the side, and so on and so forth. You might notice that the arrows are color-coded for the field's strength. So a chance to get a more intuitive feel for what's going on with a magnet and the fields around it. We're only halfway done the project. The other half I'm going to be working on in this winter semester. And this is one thing that has been started already, is a dynamic representation of the magnetic field. In this case, we've got a set of filings, you could imagine, or the arrows here. And Jared's moving around the virtual magnet, and we can see how the field is changing in real time to show, how things react to magnets. So we're going to be building on this. What's next? We want to change the marker to a three-dimensional object instead of a 2D sheet of paper, because this will allow a student to fully rotate an object that serves as the placeholder for the magnet. And then they can observe that, placeholder magnet from all sides, as opposed to just looking at the top surface of a piece of paper. We also want to implement other methods of visualization, show different kinds of magnets. For example, one thing that some people have been very excited about is they could use this to show the magnetic field of a particle accelerator. We want to get this working on other operating systems and fix all the bugs. So that's basically what we've developed. This was supported by an open educational resource grant from the Center for Teaching and Learning. And I'd like to acknowledge Krista for all her work in organizing this and helping us apply for it. Jared, who's our primary coder and our intern, and Kyle, who's the Department of Physics lab coordinator and a co-applicant on this grant. Thank you very much.